All right, thank you very much. So again, my name is Ben Marlin. I'm visiting from the University of Massachusetts, Amherst, where I co-direct and founded the Machine Learning for Data Science Lab. So this lab focuses on core problems in machine learning, motivated by applications in a number of different areas, including computational social science, computational ecology, and health data science, which is what I'm going to talk about today as an application context for the methodological work that I'll present, which is in learning with uncertain labels. Right. So within the area of health data science, it's quite broad. My group works on two different things. The first is analysis of clinical data. So in particular, analysis of ICU electronic health record data. What I'm going to talk about today is actually motivated by a different application domain, which is mobile health. So how many people have heard of mobile health? Let's see hands. Okay, so mobile health is a really broad area. It cuts across a number of different sort of types of settings. Setting that's of most interest to my group and to a number of other groups as well is one in which we sort of envision having access to the kinds of data that you would have in an ICU, sort of intensive longitudinal physiological and activity monitoring, but from people in a free living environment. Right? So over the last 5 to 10 years, advances in mobile sensing and mobile computing technologies have really sort of started to realize the possibility of this kind of intensive longitudinal physiological and activity monitoring in free living environments. So starting with a smartphone as sort of a computational platform, looking at things like smartwatches that now are imbued with quite a number of different sensors, and then moving on to more specialized types of devices, so respiration, electrocardiogram type chest bands, computational eyeglass platforms. There's lots of different modalities and devices that are on the market and that are sort of accessible at this point for use in research. Right? So a number of these devices are able to generate raw data, which is what we're most interested in. So a Fitbit will give you something like the number of steps that you took today. But what we're interested in are things like the raw accelerometry time series that come off of wristband sensors so that you can do things like gesture tracking for particular types of gestures. Right? And then at the top end, the behavioral and health researchers are interested in a wide variety of sort of driving behavioral and health science applications and problems. So things like cigarette smoking, congestive heart failure, heart disease, detection of overeating, stress, and so on. Right? So there are a large number of these different applications that are of interest in mobile health. Right. So if you look at this, this picture of raw data across these different sensing modalities, if you've seen what the data looks like, this is example data from a respiration chest band looking at inhalation, exhalation. There's a big gap between that and the kinds of inferences that we're interested in this domain, these sort of large-scale health and behavioral science problems. Right? So what's going to come in to bridge the gap is machine learning and data mining. Right? So we've got raw data. We want to get at these higher, sort of larger scale inferences around particular driving health problems, but it's a big gap, right, that we need to address. So what we've been focusing on over the last number of years specifically are examples of detector learning in this space as just a ground sort of initial problem to look at studying some of these different types of behaviors and health conditions of interest. And we'll look at how we can build on that in a second. But just to formalize, I'm sure everyone here is familiar with this, but just to make it concrete, so we're sure we're all talking the sort of same language and the same vocabulary. A detector learning problem, we're going to assume that we have a time series being generated by some dynamical system. At every time point t, we're going to assume that we have a feature vector, xt, that exists in some d-dimensional space. And our goal is going to be to infer whether or not some particular event of interest occurs or not at that time point. Right? So that captures the sort of detection version of these problems. Can I detect impending readmission for a heart failure patient? Can I detect stress? Can I detect smoking? Can I detect episodes of eating or overeating? And all kinds of other problems as well that are of interest in mobile health. So detection of drinking, physical activity, conversation, drug use. There are a whole number of these problems that start with detection as sort of the base problem. Right? So detector learning is a fundamental technology, sort of machine learning methodology in this domain to understand when things are happening on the basis of the kinds of sensor data that we can collect. Right? So I'm going to talk a little bit about the detector learning process instantiated in this particular domain, and then we'll look at how this problem of learning with uncertain labels is motivated out of this area. Right? So first, again, why are we interested in this? So if we can learn accurate detectors, we can do intensive longitudinal monitoring. Right? So we can look at when are these different high-level activities occurring throughout the day by continuously sensing and continuously running detectors. More interestingly, we can look at interventions as well. right? So in behavioral science, there are a number of sort of emerging intervention paradigms that are leveraging mobile computing and the ability to do this kind of intensive longitudinal sensing and monitoring. So in particular, there's a framework called just-in-time adaptive intervention, which is all about using real-time detection to infer context variables to use to trigger an intervention. For stress, you could do something like pop up a breathing app or something like that, right? A stress reduction app on your phone. You can also do more costly interventions like trigger a call from a health provider to a patient for a check-in, okay? So that might have a clinical outcome that, again, has a real sort of cost associated to it. Causal analysis is something else that's of huge interest here from the behavioral science and the health perspective, where if we can understand, if we can first of all detect things happening, then we can start to look at what are the causal influences, and again, maybe down to an individual level. So for example, if we want to know whether stress is a cause for a particular person to relapse when they're trying to quit smoking, right? First we need to be able to detect stress. Then we need to be able to detect smoking. Then we need to be able to look at a variety of other contexts and try to figure out sort of what the causal pathways are. And again, you can do that at a population level, but what's of more interest is to do it at an individual level. But everything is sort of founded on this idea of just trying to detect the underlying events occurring in the first place, right? So the sort of generic detector learning process is the same across all different areas, but I'm going to spell it out here again, and we'll talk about how it contextualizes here specifically. So in this domain in particular, as you can imagine, this is on-body sensor data. If you're moving around in a free-living environment, there's all kinds of noise in this data. For reasons of costs, there's interest in deploying the cheapest possible sensing devices so that things can reasonably scale. So there's a data collection, label collection, data cleaning, feature extraction sort of pipeline. You have to choose some family of detection models you're interested in, and then you have to learn one of them on the basis of that data. Right? So that's your typical training scenario, as you'd see anywhere. Testing, similar thing, right? We're collecting our data, cleaning it, extracting features, applying our learned detector, evaluating performance. As usual, you might want to go back and refine your models. You might want to refine your feature extraction step. This is not sort of academic machine learning in many cases, so we want to actually deploy into some sort of a field environment to evaluate performance at the end of the day, right? So you actually field your detectors on people ultimately, and then some application to monitoring or intervention, causal analysis, one of the examples that I just mentioned, right? So one of the ways that this differs from many other applications is that because we're talking about collecting data from people, between subject variability is a huge deal here. So if you're talking about health and physiology, there's a certain amount of variability when you look across people. When you're talking about behavior, there's even more variability, right? So when you're looking at inferring different types of behaviors, you might want to do this in a way that's sort of within person. So we try to learn a personalized model just for you that predicts some particular behavior that we're interested in, right? You can also do it at a population level as well, and you can look at building models across people. So there are different experimental scenarios that you would use depending on which of those you're interested in, right? Whether you're building something that's within subjects, so just for one person, or that you want to operate across people, right? So that's already a little bit of a difference in terms of how you set up training and testing splits, how you might do something like cross-validation when you're looking at selecting hyperparameters or doing model selection, right? But there are a number of additional challenges in this domain beyond just sort of defining appropriate experiments to measure the generalization error that you're interested in for your particular application scenario, right? So the first is actually not specific, and that's the need for high accuracy. So we'd all like to have high accuracy detectors that have high specificity and high sensitivity. In this particular space, like if you're doing something like a Fitbit, predicting steps or inferring steps per day, that's not such a big deal if you make some mistakes. But if you're sort of initiating contact with the healthcare system, health provider contacting you or reverse direction or recommending admission or clinical visit or something like that, that has real costs associated with it, both for false positives and for false negatives, right? So like I just said, cost is a big deal here. There are multiple factors for cost. So you're fielding devices, like I said, you could put better devices on people, it costs more money. The compute costs money. Communication costs money. So if we're sending stuff over, over 4G networks, streaming data into a cloud or something, that's more expensive than doing computation locally. there's a cost just for obtaining labeled data in the first place, right? So I'll talk about, instantiate this in the smoking detection setup in a second, but any kind of labeled data you want to collect here, if you want it to be a reasonable proxy for ground truth, it's going to be expensive, right? You're going to have to bring people into a lab setting, you're going to have to observe them, you're going to have to compensate them for involvement in these studies, right? There isn't really an opportunity to crowdsource labeling in the sense that there is in areas like computer vision for object detection, right? So you typically can't look at this data post hoc and understand what's going on in it. We just don't know what to expect in the data. With respect to subjects involved in these trials, cognitive burden is another thing. So you can ask people once a day what they were doing all day long, but they're not going to remember. So there's recall bias and self-report. You can have people, again, either self-report, you can do lab-based sort of chemical analyses. So you can look at biomarkers for things like smoking or stress, but that involves taking cheek swabs or poking people with needles and taking their blood out. So that's not something you can do intensively and longitudinally. And then there's also energy cost. So because we're talking about mobile systems, when you're fielding devices, you have to worry about the energy cost of sensing and communication and computation, and all of these things sort of trade off against each other. So the key problem here is, given all these constraints, how can we increase the accuracy of detectors without substantially, or preferably at all, increasing the costs of sort of energy and computation, subject burden, and all these other factors as they are, even decreasing them further, okay? And so this is where the sort of machine learning-based data analytics can come in and sort of leave the other factors flat and try to look at solving problems here, providing more accurate detectors by leveraging aspects of domain knowledge, more advanced feature extraction, various kinds of sort of strategies to leave everything flat, but improve the accuracy of the resulting detectors, right? So that's sort of the name of the game. There are all kinds of different methods and strategies that you could take here. There are all kinds of sort of lines of research that you could look at pursuing here. So the one that I'm going to talk about today around uncertain labels has to do with weakly supervised learning, right? So natural language processing in other areas, weakly supervised learning is starting to gain some traction. The basic idea is, in many cases you can't get direct labels for the objects you'd like to label. It's either too costly or it's not practical. So the question is, what can you use as a reasonable proxy, right? A reasonable sort of weak label proxy. And so in this setting, what we're going to see is that getting very precise labels for short timescale events is actually really costly and still sort of subject to some error. So what we'd like to be able to do is sort of loosen that up a little bit, allow some noise in the labeling process, and still be able to learn something that's useful at the end of the day, right? So that's what this, the methodological component around temporally uncertain labels and learning from them is about, okay? So in terms of the specific application domain, so this is a problem that occurs in eating detection, smoking, drinking. There's lots of different areas that have a similar kind of flavor. So I'll focus on smoking detection as an example. In this domain, what's of particular interest is building detectors that have an intermediate layer where they look at detecting sort of atomic events. And for smoking, those are individual smoking puffs, right? So I'll show you in a second what some of the raw data looks like. It's plausible, right, that you can detect smoking via smoking puffs when you're looking at respiration data because it has a particular signature in that data. That's not so hard to pick out. So in the presence of noise, as you're moving around and doing other things, there are lots of confounders, right? So talking is a confounder, any kind of physical activity can confound the detection problem, right? But it's plausible that you can see the right features in that data, right? So what we're going to do is instrument people. We might put an accelerometer, sort of wristband on them to look information. We might put a respiration monitor on them, like I was just saying. So you can collect the sensor data this way. Again, if you ask people to self-report when they were smoking, they can't do it at all accurately in a way that's useful, right? So you're not going to get someone to self-report individual smoking puffs, right? It's not going to happen. If you ask people to self-report start-end times for sessions, maybe it's going to work. If you do it at the end of the day, they're not really going to remember. So you have to sort of leverage, again, some more advanced machine learning methods. The way this is being done right now is to conduct this whole process in a lab setting. So you bring someone in, you give them a script of different things to do. You have an observer watch them. All right, so for the smoking detection piece, what's going to happen is every time the subject takes a puff on the cigarette, the observer is going to click a button on the phone that's logging the data. So you have aligned, well, you have the sensor data, and you have the stream of positive event labels associated with it. All right. So that's what the lab setup looks like. If we drill down and look at the data, what does it look like, right? So what's going to happen is the trial starts, some data starts coming in. For the case of respiration data, you don't need to look at applying a detector like time point by time point, right? So this data, depending on the sensors, might be 20 to sort of 200 hertz for the underlying waveforms. You don't need to classify every individual time point in that data. So you can look at segmenting it into respiration cycles, which you can detect in an unsupervised way, or you can build a sequence on the peak inhalation points and look at associating labels with those. So in this example, I'm going to look at respiration cycles, which is characterized by sort of an inhalation to exhalation loop. So you can get it via zero crossings, maybe with some filtering. There are lots of different ways to solve that part. That's not the focus, right? So in this case, again, we'll just imagine we've windowed the data according to one of these approaches. And we're going to look at trying to learn a detector on these windows. So we'll take a window of data, extract some features, and try to make a prediction. Right? So what happens here? So this chunk maybe is not a smoking puff, right? So our observer wouldn't do anything. Next piece of data comes in, again, not a smoking puff, so nothing happens for the observer. Let's say in the third respiration cycle, let's say is a smoking puff, right? So it's characterized by, in this case, a very clean example, higher amplitude inhalation, higher amplitude exhalation, somewhat longer duration. In the absence of noise, again, these are not that hard to pick out in some cases. So this is maybe a positive, right? So what we're showing here in colors are what are the true labels on the windows, right? So this respiration cycle really was a smoking puff. But what happens with the observer, right? So the observer can't see the respiration data. They're just watching the person, right? So what's going to happen is every one of these positives is going to induce some kind of probability distribution over the time axis, right? In this case, a normal distribution just for sort of illustrative purposes. Right? And so when the observer clicks the button to indicate the smoking puff actually happened, that's going to be some draw from this distribution. Right? So we're going to get some single timestamp as a realization of this uncertainty over the time axis for where the positive event actually occurred. Right? So as data continues to stream in, we're going to have negative examples, we're going to have positive examples. Every positive is going to generate some distribution over the time axis, and then you're going to get some sample from that, basically, indicating where the person clicked the button, right, to indicate the positive event occurred. All right, so what's the challenge here? The challenge is, at the end of the day, right, you lose all associations, right? So this is the generative process in theory. What you actually see is this, right? You get the raw sensor data, you can segment it or you can window it as you like. You have this stream of continuous time labels, right, indicating where the positive events occurred. So it's just a stream of timestamps indicating where the positive events were entered by clicking, right? And now you need to learn something on top of this, right? So we want to learn a detector that takes a feature vector and predicts the label, but we don't actually have labeled windows, right? We have these two sequences which may not actually be in proper alignment. So you can assume that the negative alignment isn't too bad, and you can drop it down on this sequence, but it will incur errors, right? So the events that we're labeling are like a second long or 2 seconds long. And so if you're off by a second, your positive label ends up in the wrong place, and you turn the uncertainty or the noise in the timestamps of the labels into noise in the values of the labels projected onto the underlying sequence, okay? So that's the key idea. You can't just, in this presence of sort of temporal noise, once it gets larger than sort of the typical boundaries, 1 or 2 seconds, for the respiration cycles, you can't just drop the sequence down if it's got noise in it, or some of the labels will land in the wrong place. So let's see, here's this one. Let's see. So the third one there, for example, it should have been a negative. It ends up being a positive. The first positive that's highlighted should have been a positive, but the one before that also should have been positive. So the sequences get out of alignment because of the temporal noise. Right? So our challenge is, how do we learn something on top of this, right? Without assuming the naive alignment is actually correct. Right? So how do we make that a little bit looser? So the basic idea here is, let's jointly model both processes. So I just gave you a generative description for the observation process. How does the underlying sequence of data and true window labels map into the observed timestamps, right? The detection process, right, the detection model that you can add into this just looks at what are the feature vectors, and then what are the labels associated with them. So anything that you want to use there, you can drop in to the framework that I'll show you. So I'm going to illustrate this with logistic regression, but if you want to use a multi-layer neural network, or if you want to drop in an LSTM or something else more fashionable, then you can do that, kernel logistic regression, whatever. you can drop in anything as that detection piece, and the extra piece we'll model is this part about the observation process, right? Tying the underlying waveforms to the continuous timestamps, right? In a way that's more flexible than just assuming this sort of they should line up exactly. Okay, so I'm going to talk about the model, starting with some notation. We'll move through the form of this joint model. I'll show you how learning and inference works, and I'll show you some results and experiments, and then some extensions. Right? So how do we set up the notation here? So as we said, every time point, right? Every window has some feature vector associated with it. So we're going to assume we have n time series, right, corresponding to sessions of data collected from different people or different sessions from the same person. Every one of those time series will break it up into some discrete sequence somehow. For every window in that sequence, we'll have a feature vector associated with it. Right? So xni is the feature vector for the ith window in the nth time series. We also need to keep track of where these windows occurred. Right? So we need to keep track of, let's say, the starting point for each of the windows. So in the example that I was showing, we were doing pre-segmentation, so the windows are of various sizes. It's not standard, uniformly spaced, discrete time data. So we'll keep track of the start point. You can take the midpoint. It's not a critical decision, but you need information about where the windows were in the series. Right? Every window has a label. Right? This is what we actually want to predict at the end. So for each of the windows, should it be positive or negative? As a modification to the basic process that I described, to make it a little bit more realistic, we'll also assume that every window generates some number of observations, possibly 0, 1, or more, right, in a way that's conditioned on the true label. And the intuition is, if you're a positive window, you should probably have one positive event associated with you, but it's possible the person the observer looked away for a second and then missed a smoking puff, right? Or they might have accidentally clicked twice or something like that for the same positive. So to make it a little bit more flexible, we introduced this extra layer where every window, again, is associated with an observation count, both the positive windows and the negative. So you can model false positives and false positive rates. You can model false negatives as well using this component. Right, we'll see how the pieces fit together in a second. And then the last piece is the set of observed timestamps for the positive events. So X's feature vectors, T's are the timestamps, Y's are the window labels, O the number of positive events per window. And then the Z's, again, are the timestamps of the positive events. So the X, T, Y, O, there's the same number of those. So if our sequence has L windows in it, there's L of each of those. There's L feature vectors, L starting times, and so on. The last one has a different number of elements in it, right? So we'll say there are M different observed positive timestamps for a particular chunk of data, right? So usually in the lab setting, and we'll see some real examples, but the non-smoking data outweighs the smoking data by many multiples, right? So this is heavily class imbalanced data. In the real world, it's even more heavily class imbalanced. So if you smoke 3 cigarettes a day, average number of puffs per cigarette turns out to be about 12. So you have 36 respiration cycles that correspond to positive events. You take a breath every 1 to 2 seconds. So there's many, many times more negatives than positives in the data, right? Okay, so in terms of the model, how do we build a model on top of this? What are the pieces, right? So the joint model, we're gonna look at so we'll condition like a normal discriminative learning on the features, and in this case also the time points that generated those features. And then we'll build a joint model of the true labels, the number of positive events generated by them, and the positions of the positive event timestamps, which are the Z's, right? So the thing to remember is that these xni's are individual feature vectors, tni's an individual time point. This model looks at entire sequences at a time. So the xn is the sequence of feature vectors, tn is the sequence of time points, the yn is the sequence of window labels. So we're modeling one whole time series worth of information at a time, right? The n's, again, indicate different data cases, right? So every data case is a time series here, just in terms of what's going on with the notation. So again, these are all the window times for sequence n. These are all the feature vectors for window n. These are all, this is the set of event timestamps. This is all the observation counts. This is all the window labels, right? So to do something useful here, what we're going to do is break this distribution down into some chunks that we can model, and that will allow us to build a detector that we can subsequently use and forget all the extra stuff here, right? Which will be quite convenient, all right? So we're going to break this down into 3 pieces. The first piece looks at the probability of the label given the feature vector, and And so that's a standard detection model. So this piece will actually decompose across the sequence so that once it's learned, you have an independent detector like you would normally get by applying an SVM to the windows or by applying logistic regression to the windows or applying a neural network to the windows. Okay? So this model will learn this component with these additional pieces supplied. And then at the end, you'll just be able to extract this piece that is the detector and use it, right, as if you trained it on labeled data in the first place, normally labeled data. Right? The second piece is the observation count model. So this might be something like a Bernoulli. Depending on the label, you have some coin flip probability that tells you whether you'll generate 0 or 1 observations. Right? So that Bernoulli probability then is going to be your false positive or false negative rate sort of directly. You can also generalize this to build distributions of, you can put a distribution over more numbers of possible observations generated by a window. So if you thought there might be 1 or 2 or 3 positives associated with a single window, you could do that and learn that back. The last piece is the observation timestamp model. And at its core, this might be something like a Gaussian distribution. So if you knew a particular window with a particular starting time was responsible for generating a particular observation, the model might be something like a Gaussian distribution centered at the start of that window. Is essentially what I was showing on the sort of motivation slides. Right? So those are the 3 pieces of the model that we're going to learn. An example model is something like this, right, as I was saying. So the y and I given x and I might be a logistic regression. O and I given y and I might be Bernoulli. The timestamp generation process given, so where the click occurs given the timestamp for the respiration window might be something like normal, right, again, as an example. So the problem is we don't have the pieces that we need to learn this, right? We don't have all this data. So we know the x's, we know the t's, and we know the z's. The sequence of observed timestamps, we have that. Feature vectors we have. Their time points we have. The true window labels we don't have. The number of observations per window we don't have, right? So we have a joint model, but we don't have all the values of the random variables that we need to learn. If we did, this problem would decompose into learning a detector like you normally would with the feature vectors and the labels. You'd have these other pieces, you could learn them, but you wouldn't actually need them, so there wouldn't be a point, right? So here the key is we don't have the observation counts, we don't have the window labels. We just have features, timestamps, and this set of continuous time positive event markers. Right? So how do we learn the whole thing? Right? Okay. So what we're going to do is we'll do maximum likelihood for this, as is usually done for probabilistic models. What we're going to do is take a log likelihood, sum it over all the data cases we have as you normally would. But the form of the model is going to look at the probability of the set of positive event timestamps, the z's, given the features and their timestamps, right, their locations, and that's it. Okay? So what we're going to do is try to learn these pieces, right? But all we have are these 3 pieces of information. So the way you do this is to look at marginalizing out the things that you don't have from the joint model, right? So we can drop the joint model in here that includes the labels and the observation time counts. We don't have them, so we'll marginalize them away by summing them out to form this, marginal likelihood optimization problem. Okay? So wrote down a joint model of the entire process. We sort of imbued it with our domain knowledge about how the observation process works, up to some parameterization. Then we'll marginalize out the pieces we don't have to learn all 3 models, right, simultaneously. Once we have all 3, we'll subsequently throw out the last 2. There's interesting information in them, but from a detection point of view, we don't need them. We'll just take the model for y given x, and then we'll use it as a detector. Right? That's the idea. So as far as learning goes, the key thing for these kinds of marginal maximum likelihood problems usually is marginal inference. So if you can solve the marginal inference problem, essentially computing the probability of z given x and t, and other marginals like y given x and t, then you can solve the learning problem, right? So this is a common characteristic of this kind of model. If you can do inference in the model for the right quantities, then you can learn. If you can do inference efficiently, you can learn efficiently using standard sort of gradient-based methods, right? So I'm not going to go over the inference process in detail. This work is based on a paper that was published at AI Stats this spring. So if you want to see the details, you can look there. The basic idea is you can do inference via dynamic programming in this particular model. If you don't have constraints on the observation count process, the time for inference for a single sequence is m squared L, where m is the number of positive event labels, and L is the length of the sequence. If you assume that there are only 0 or 1 positive events associated with each window, then that actually drops down to O of ml, right? And that's not an unreasonable assumption. There's still enough slack that you can make up for some missed observations by assuming they were generated by other windows and things like that, right? So in practice, we use this sort of Bernoulli observation process. You have a runtime that's sort of bilinear in the number of positive event labels, which, as I said, is going to be small, right? So even in a session where we're watching people for half an hour or something like that, there's going to be tons and tons of respiration cycles. Few will have positive stamps associated with them, right? So M is going to be much less than L, and you can, this is going to have a running time that's more like dependent on the length of the sequence than on M itself, right? So the intuition for the program is sort of similar to the sum product algorithm, and you can kind of see why. This is a sum, this is a sum product kind of form. What sits inside the P of psi piece is a product. The reason this ends up being something that looks sort of close to linear time is for a similar reason that you get a linear time result for conditional random fields for chains, right? So this model's not exactly, it's not a chain structured conditional random field, but it has a right branching dynamic program, right? So you get a similar kind of analysis. Okay, just to give you a flavor for how the result works out. Okay, so that's the basic setup, right? So we have this particular observation process. We build a generative model of it. We combine it with our discriminative model for our detector. We'll jointly learn all the pieces by maximizing the marginal likelihood. And then at the end of the day, we can sort of keep the detector model that we learned using this process. We can throw the other stuff away. Again, there's maybe interesting stuff to analyze there in terms of what the observation process actually is. Might give you some information about how you might want to, let's say, refine your study protocols for how data is being collected. But for these purposes, really what we're after is just the detection model itself. Right? Okay, so I'm going to talk about some experiments and show you a little bit about the performance of this approach, and then I'll show you some extensions that we're working on currently, and then we'll wrap up. So in terms of experiments, data of the form that I've been describing exists, right? There have been a number of papers that collect data of this type. There are recent papers looking at eating detection, drinking detection, smoking detection, which is what I'll focus on here. The observation process that I described for what happens in the lab really is what happens in the lab for the data sets that I'm showing here. So these are relatively small data sets. As I mentioned before, data scarcity is one of the largest issues in this domain. It's expensive to collect data. It's expensive to get large number of participants through protocols. The two data sets here, one collected data from 4 people, the other from 6, right? So you have to be careful about generalizing beyond these small populations. The first data set had 13 sessions, so that means each of the 4 people participated in multiple sort of smoking session experiments. The second data set had 30 sessions. You can see the number of positives and negatives on there, right? So the first data set, 179 positives. These are respiration labels, respiration cycle labels, 3,180 negatives. So very, very class imbalanced. The other has a similar balance, right? It's more data. So what's interesting is that both data sets, in order to build something that was useful, the study personnel had to go back and sort of manually realign the labels sort of in a very local sense, right? So they looked at where the observers had clicked. They tried learning models using that, and it just didn't work very well. They went back in and looked at the data and realized that the problem was the labels were off. They were doing this naive alignment process exactly as I described, and realized that the labeling, the sort of temporal granularity of the labeling, the temporal accuracy wasn't high enough to actually learn good detection models on this data. It's very common in this data to have a smoking respiration cycle followed by non-smoking. And so if you're off by like a second, your positive label drops onto a negative example, and learning's just not going to work. Right? So they went back in very painstakingly, realigned the labels using all the data that they had to try and sort of pick up in places where they could see the inhalation-exhalation patterns that I described, to try and sort of align the labels better with those. Right? So that's ground truth in air quotes, right? So it's possible, again, that the research staff that went through and performed that realignment could have made mistakes, right? It's not perfect, even though there's additional manual effort at great cost to clean this up, right? What's of interest for us for looking at this particular process is that both data sets had this manual realignment applied. The original labels for the first data set weren't preserved, but for the second they were. So we have both original labels as recorded by observers and realigned labels as sort of a proxy ground truth from study staff. So we can compare those two conditions to each other. We have what we can sort of use as ground truth labels for testing. We have good labels for training. We also have noisy labels for training, and we can look at what happens when we use them in different ways, right? So let's see. In terms of the experiment details, you can do interesting sort of quasi-synthetic experimental designs here, where you can take the timestamps that were cleaned up, and then you can add noise back into them, right? So it's the original feature vectors. It's the right labels, but you can make different assumptions about what happens with those labels. You can move them around relative to their sort of true positions under different assumptions, and then you can look at what happens when you try to learn back from there. You can look at the degradation in performance. You can simultaneously do the same thing with the numbers of observations. So you can like add a filter where you flip a coin for every positive label, and you can hide it as a false negative, right? And you can look at what happens there. Again, as I said, for the second data set, we have both original noisy labels and the aligned labels. So we can train on the unaligned labels, and we can test on the realigned labels and see what happens. As I mentioned before, we're just going to use logistic regression. There's a sort of large feature expansion that's applied here, so it's not a linear logistic regression. It's on top of a basis expansion. Those details, again, are not important for this part of the process. And so we'll compare the sort of naive alignment strategy against other approaches. So multiple instance learning is something that also makes some sense here, where instead of taking the labels and applying them to individual cycles, you can put the cycles into bags, temporarily sort of consistent bags, and then put the labels on the bags and try to learn using multiple instance learning, for those of you who are familiar with those ideas, right? So it's another relaxation of the idea that the labels are going to be accurate. It's a way to reflect the idea that there's some uncertainty in which exact position the label should be associated with, but it doesn't have the sort of more fine-grained assumptions that the approach that we're proposing has, where it's actually looking at the observation process and trying to model it sort of window by window, right? But it has a similar ability to sort of incorporate some uncertainty. So we'll look at what that can do. So the first chunk here is what's happening with the noise model. So again, we have these two sources for this one data set. We have the aligned and unaligned or original noisy labels. We can look at what the distribution of the gaps is between those two, right? So every positive event has a realigned position and an original noisy position. We can look at the distribution of the gaps, and this is what you get, right? So it's not exactly normal, but for 300 samples or so, in terms of the positives, it's not bad, right? So it's sort of approximately normal. You can see that there's, the x-axis here is in seconds. So you can see there's a bit of a positive bias away from the start of the respiration cycle. So people are tending to click after the respiration has happened. And again, the visual cue for smoking is more about the gestures than about the respirations in some cases. So it's sort of understandable that you would have that delay. I mean, no matter what, there's just a question of even if you could see the thing happening exactly when it started, just the delay in time for you to see it, process it, and then click the button is going to induce some positive bias in most cases. Right? So the positive bias isn't large; it's maybe 1.5 seconds, but it's enough to sort of have this impact on learning that's quite severe. Right? So in terms of the models that we're applying here, again, it's the Bernoulli noise model, Bernoulli for the observation count model, Gaussian for the observation timestamp model, and then logistic regression for the detector that we're learning with this underlying basis expansion. Right. So what happens when you use this? Right? So there are a number of different experiments you can perform, like I said. This is one where we start with the true labels, right? Or sort of quote-unquote true labels from the realignment process. And then we look at adding noise to them from a normal distribution with varying standard deviations. So as we go across the axis here from left to right, we're increasing the standard deviation of the noise that's applied. And so the line at the top, the dark line, is the result that comes out of the model that we're proposing. The dashed line is what you get when you learn this. So you do learning using the manually realigned data, and you test on the manually realigned data. So we're actually outperforming that a little bit for the range of standard deviations that are shown here, which are up to 5 seconds. The reason for that is what I said. It's quote-unquote ground truth data, right? So they realigned the positives that were input against the data that was there, but there are possibly false negatives in the original. The person didn't click, and so there's no timestamp associated with the with those events, and so the relabeling process sort of didn't pick those up, right? So they weren't adding labels, they were just moving the timestamps around. And so because this model has the ability to both pick up sort of false positives and false negatives and sort of essentially reclassify the labels that were input, you're able to get some lift even over this process that's supposed to be ground truth, right? It's not a lot, but it's some. In terms of F1. If you look at the other approaches, so the lines that are below, one is the multiple instance learning-based approach. It drops off relatively quickly, but it does better than just assuming that a naive alignment as you add noise, which is the line that drops off sort of precipitously down towards 0, right? And again, that's driven by the fact that the positives are sparse amongst the negatives, and so if you're off by a second or two, which is what's going to happen when you get up to standard deviations on the temporal noise of 2 or 3 seconds, the performance is going to drop way off, and that's what happens. Right? You can also look at this process of keeping the labels in their true positions, but varying the true positive observation probability, so or the probability of observing a timestamp, right, given the window label. And so here, if you reduce the probability of seeing a positive, right, the performance drops off for the other methods. But again, we're able to stay somewhat stable. And the reason is the model is able to sort of, as it sees some examples of positives, it's able to understand other things that might also be positive and recognize them as false negatives and sort of allow them to be interpreted in that way, which stops the model from sort of confounding positive and negative window labels, right? So this model has quite a bit of flexibility in terms of how it interprets the data. You have to carefully control that. So again, the model makes an assumption that the true labels aren't going to be too far from the positions where they're observed, and that most of the time you're going to have, if you're in a positive window, you'll have just one observation. Those are added in as prior distributions on top of the structure, but it's still flexible enough to figure out sort of what are the optimal parameters within that setup. In terms of the detector learning problem, this is what it looks like. So again, you can outperform learning on manually realigned data using this process because of the noise issues I was talking about before. The multiple instance learning and then logistic regression with naive alignment suffer heavily. And again, these are real data results, right? So this is learning on the real noisy data, not synthetic, testing on the realigned data, and then looking at what happens, right? So we're getting substantial boosts in performance. This is still not, in terms of overall F1, these are not super detection accuracies. This is just based on respiration. So there are a number of extensions here looking at additional sensing modalities to boost up the F1 that you can get out. But the key thing is that if the labels are misaligned, it doesn't matter what the features are, right? You can improve the performance under the approach that we're proposing here by having better features. But if the labels are not lining up properly with the feature vectors, any method that assumes that they do is going to suffer no matter what the features are. Right? Okay, so that's the story. What about future directions? Right? So there are a number of simplifying assumptions here. I'm just going to talk through a couple of possible ways that you can extend this in different directions. The first one is we just addressed the problem in mobile health that has to do with observation processes and weak supervision for data collected in the lab setting. Okay? What's of interest, though, is can we get better data in this sort of natural, free-living environment condition? So in the lab setting, you can have observers, you can watch people intensely. You're in this problem of sort of trying to predict individual or detect individual smoking puffs, but as I said, you can't do that in the field, right? You're not going to get people to self-label individual smoking puffs in the field. It's not going to happen. The typical field studies ask people different questions than what you can do in the lab. And so the question is, can we incorporate that information in a meaningful way into learning? Or can we do some mix of data from the lab and data from the field? So in the field, what can you do, right? You can ask people potentially to tell you start and end times for smoking sessions. That's about the highest temporal resolution thing that you can do, right? You have to be careful about when you ask them. You want to ask them as soon after these sessions occur as possible, or sort of use a confirmation process where if you detect start of smoking, you ask them, did you just start smoking? And they can say yes, which will help, right? But there's going to be some sort of noise, again, in this process in terms of if you ask people for start and end, where are they going to annotate exactly, right? And so it's a similar kind of process. If you're asking them to annotate start and end, depending on how the sort of logistics of that process, there'll be some uncertainty around it. You'll generate some particular start and end points if you ask people to segment. And then again, at the end of the day, you lose the association, you're back to this. Raw sensor data, start times, end times, that's it, right? With some uncertainty around how good the start and end points are, where exactly they occurred, right? That's one variant of this. Again, an even more realistic variant is you've got the data and you just ask people to tell you when they were smoking, a single point. So maybe there's some much larger uncertainty if you ask this question about what time point people are going to pick exactly. And then they return a single timestamp to you, right? And that's all the information you get. And now you have to try and learn something, right? So this is on the sort of like hierarchy of weak supervision, we're getting weaker and weaker and weaker. So we had weak labels for individual windows. This is, right, this is a weak segmentation where we're not really sure if those endpoints are correct. And then this is like even weaker. Just tell us roughly when you were smoking. We'll try to figure out something from there, right? So this is the direction that we're going in with this work right now. So how do you incorporate the kinds of information you can get from the lab with the kinds of information you can get from the field to reduce the assumptions? It's cheaper to get this kind of data from the field. We're not even sure if it's useful at this point to ask for these kinds of queries. So can you actually improve your detection model by asking these kinds of queries of users? Right, so lots of logistics about how you do this exactly. Active learning ends up being something that's useful here, right? So can we detect and then prompt instead of have people just sort of report spontaneously? In order to apply this kind of methodology in the first place, right, so if we're going to get information about segmentations, we need a model that can talk about segmentations. And so in earlier work, we have this model for hierarchical activity detection and segmentation that basically builds up through multiple layers. So it looks at individual labels on individual windows or segments, and then builds a hierarchical detection framework on top of it. And so really, like, the top level pieces are, you can interpret them as activity segments. And so this model, if you think about what's going on here, if we ask the question like this, we're getting back some information about something fuzzy at the top level. We know nothing about the bottom levels. You have to do a giant sort of marginalization to integrate over all the stuff that no one told you about, including we don't actually know what the top level is, right? We just have some idea of where the segments might occur. So we have a model that can do this kind of reasoning over segments. We're currently looking at integrating it with observation processes for different kinds of noisy segments. The model that underlies it is this sort of giant factor graph model that reasons about segmentations across multiple levels. And so you can start to see how you might incorporate a noisy observation process into this. Right? You at least have the elements you need to reason over, which are the segments, which you don't have in an independent detector model. Right? Okay, so we're just about out of time. So just to conclude, hopefully I've convinced you that there are some interesting problems coming out of this mHealth domain. It's really an emerging domain. The data in some ways don't look like data from other domains. They have interesting attributes. The constraints are interesting in terms of cost and cognitive burden, computation, devices. There's this whole range of sort of considerations to take into account. As I mentioned, we're working on different solutions in different parts of that space. In addition to what what I've presented here. One common theme from the work that we've been doing is that due to the data scarcity that exists in this domain, models that can do a good job of capturing whatever domain structure you understand often work quite well, right? So we're not the levels of data here, as you saw in the data tables, were sub-MNIST data volumes. So the idea that something like deep learning, in the absence, again, of like incorporating substantial domain knowledge is going to work well here, we're not at a point where we have enough data for that to be true. So it's definitely the case that as you can compensate for data scarcity using knowledge of structures or processes that you encode directly, that's going to tend to outperform other types of approaches. And we've seen that across a variety of different problems in this space. As we get larger data volumes, you'd expect to see things like unsupervised feature extraction to work better than manual feature extraction, to see things like LSTMs outperform things like conditional random fields on this kind of data. But with the data volumes we have now, it seems like we're not quite there yet. As I mentioned, we're working to relax some of the assumptions around the model that I presented to make it more applicable to real-world data from the field. The sort of subject self-report is easier to get than the lab-based data, but then it's harder to use. So again, we need more advanced analytics to bridge that even larger gap. Right? So that's it. Let me thank my collaborators and sponsors. So the work that I presented here today is primarily the work of one of my PhD students, Roy Adams. The data that I talked about is mostly collected at the University of Memphis. One of the students there, Nazir Salahin, did a lot of that work. Collaborators at UMass Amherst, Deepak Ganesan in the sensors lab, who I work with very closely, and at University of Memphis, Professor Santosh Kumar, who leads the NIH-sponsored Big Data Center of Excellence in Mobile Sensor Data to Knowledge. That is the primary sponsor for this work. Okay, thank you.